Hello everyone. Let's analyze. So today we're going to talk about metric spaces. What are they? And what are they used for? Well, let's start with a rather simple question. What is the distance from 9 to -7? Well, it should be pretty straightforward that the distance from 9 to -7 on the real line is just 9 minus -7, 16. Okay, well, what is the distance from -7 to 9? Well, of course, those are the same numbers. The distance ought to be the same, 16. Just as the distance from Edinburgh, Texas to Dallas, Texas is the same as the distance from Dallas, Texas to Edinburgh, Texas. A distance is a measurement without any sense of direction. It's a directionless measurement. So the distance from -7 to 9 equals the distance from 9 to -7, which is 16. So in order to put together a consistent distance formula, we typically put an absolute value around the difference. And of course, the absolute value of a difference of real numbers, that's something you've seen perhaps a dozen times every single class in real analysis up to this point. So the distance from A to B on the real line can be given by what we'll call here a distance function, and it's just the absolute value of the difference from A to B. That's one way of measuring distance. And indeed, we've measured this distance in talking about limits, convergence, pointwise convergence of functions, convergence of sequence. Note, the only number a distance of 0 from A, well, is A itself. Now, what about in 2 dimensions? How would we measure distance? Consider a point X and a point Y in 2-dimensional space. What's the distance from X to Y? Well, Pythagoras might suggest measuring the distance as the bird flies. He might use, in fact, his famous Pythagorean theorem to suggest that this distance is the square root of the sum of the square of the sides of a right triangle. So we just take the distance in the x1 direction, the distance in the x2 direction, square each, and take a square root. Sure, that works. That's one way of computing distance. You may look at this formula and think that these absolute values are superfluous. Well, you'd be right if these were real vectors, which our setting is. Of course, if we were to extend into vectors with complex entries, then these absolute value signs would be necessary. So we have one suggestion for measuring distance. We can even generalize it to n dimensions. Now, let's make a quick note here. If instead of the crow flying directly from X to Y, the crow took a detour to Z, then the crow flew a further distance. The distance from X to Z plus the distance from Z to Y is longer than the straight shot. This is what's known as the triangle inequality. So just a quick note and how Pythagoras would measure this distance. But a taxicab driver might beg to differ. A taxicab driver might say, look, if you want to measure distance as the crow flies, hire a crow. I'm not taking that route. I'm driving east along the streets and north and south along the avenues. Your fare is this distance plus this distance. And I don't really care what Pythagoras or the Crow has to say about it. Well, that's another way of measuring distance. Measure distance in the one direction plus distance in the two direction. And of course, we can generalize this idea for measuring distance as well by just summing the difference, the absolute value of the difference in every component direction from 1 through n. So if there's more than one way to measure distance, what are some ground rules? What makes a distance function truly a distance function? And since you're talking about generalizing ideas of how to measure distance, well, what else can I actually measure? So let's generalize this idea of measuring distances. A set X, right? A set of what? Well, a set of things. We'll talk about what different kinds of things we're going to discuss, but for now, an arbitrary set X imbued with the metric or distance function is called a metric space. Okay, well, what's a metric? What's a distance function? But what are the ground rules? So that when we say distance, it makes some sense in how we tend to think about distance between two elements. Well, a distance function is a metric. A distance function is a metric on x if for any two elements x, y in my set x, the distance between x and y is not negative, and it's only 0 if x and y are the same. In other words, if the distance from x to y is 0, x and y must be exactly the same. The distance from x to y is the same as the distance from y to x. Right? That makes sense in how we ought to measure distances without any sense of direction from x to y or y to x. And the third is, well, the triangle inequality, or the idea that detours are longer unless, of course, the detour is on the way. The distance from x to y is less than or equal to the distance from x to z plus the distance from z to y. Again, we can visualize this inequality as one side of a triangle is less than or equal to the sum of the other two sides of the triangle, which is why this is often called the triangle inequality. So let's give a few examples of metrics in Rn. Well, one we've already talked about, the famous taxicab metric. Another is one that you ought to be familiar with, the Euclidean distance. Of course, we could derive it from Pythagorean's theorem. And another is what's sometimes called the infinity metric or the infinity distance function. It's the maximal component of the absolute value of the difference. Now, let's show that that third metric is in fact a metric. That if I define the distance between x and y to be the maximal component difference in absolute value, let me prove that this actually does satisfy the definition of what I mean by a metric or a distance function. So first, let's show that the distance is greater than or equal to 0, and is 0 only if I'm measuring the distance between, well, two of the same vectors. Well, for each entry of my vector, the absolute value is bounded below by 0 because I'm taking, well, an absolute value. So 0 is less than or equal to the absolute value of the component difference. And of course, for each k, the component difference in absolute value is less than the maximal one, or less than or equal to the maximal one. Now, if the maximal one is 0, well, that happens if and only if xk minus yk is 0 for every k, because I have that this term is sandwiched above by 0 and below by 0, meaning it must be 0. And if the component difference is 0 for every component, well, then every component is the same and x is equal to y. So this is a typo here. What I meant to say, show that the distance from x to y is the same as the distance from y to x. But we'll go ahead and show it anyway. Since for each k, xk minus yk equals yk minus xk for every single term, well, then it's also true for the maximal term. And of course, the maximal term is the definition of the distance from x to y, or the distance from y to x. So hopefully we see why that one was pretty straightforward. Now we want to show the triangle inequality. Well, given that for each k, the absolute value of the difference of the kth component is equal to, well, itself if I add 0, and I'm going to add 0 in this form, by adding zk and subtracting zk, that is the kth entry of some vector z. Well, then I can apply my old-fashioned triangle inequality, because this is just the absolute value of the sum of two numbers, xk minus zk and zk minus yk. So the triangle inequality says this is less than or equal to the absolute value of the difference between the kth component of x and z and y. And of course, for each k, the absolute value of xk minus zk is less than or equal to the biggest one. Same thing for the absolute value difference of zk and yk. And of course, that is the distance from x to y using this infinity norm. Similarly, this is the distance from z to y using the infinity metric. And since this inequality is true for every k, it's true for the maximal k, which is the distance from x to y. And that proves a triangle inequality. Okay, so we can measure distance between numbers, between vectors. What about functions? Yes, we can. Let's consider a set of functions. How about this one? The set of every continuous real valued function on the interval a to b. All right, so there's a set, right? That's a set of functions. How would I measure the distance between two functions? Well, here's one way, is I could take the supremum of the difference in absolute value. Notice that kind of looks like the infinity metric on our vector, our vector space Rn. So hopefully it's clear that the distance function given here, that is the metric, is not negative because of the absolute value. It's 0 only if f and g are equal for each x, that is, f and g are equal. And that I could switch places with f and g because of the absolute value and get the same outcome. So then let's just show the triangle inequality. Of course, as you can imagine, it's going to be very similar to the previous demonstration. For all x in my interval, f minus g is equal to f minus g if I just add 0 by way of adding z and subtracting z, where z is some function in my space, in my set. A triangle inequality says this is less than or equal to f minus z, an absolute value, plus z minus g, an absolute value. And of course, the difference between f and z is less than or equal to the smallest upper bound of all differences. Similarly for the difference between z minus g. And then the smallest upper bound, the supremum, well, that's actually the definition of the metric between f and z, and the metric between z and g in the second term of our sum. And since the sum of these two metrics is a upper bound for the difference between f minus g for all x in my interval, then this upper bound is greater than or equal to the smallest upper bound, that is the supremum of f minus g, which is the definition of the distance between f and g according to this notion of measuring distance. So again, this exhibition was pretty much the same as the previous for Rn, but now we're just dealing with continuous functions. Now let's note real quickly the similarity between Rn, what we think of as the canonical vector space, and this space. Well, if I have two vectors in Rn and add them up, I get another vector in Rn. And if I have two continuous functions and add them up, I have another continuous function. Similarly, a scaling of a n-dimensional vector is still an n-dimensional vector, and a scaling of a continuous function is still a continuous function. So in fact, the set we're talking about in this example is in fact a vector space. Now, this same metric can also be used on as a metric on the sets of bounded functions from A to R, and the set of continuous and bounded functions from A to R as well. And this distance function would still be a metric. Now, since we now have a general way of measuring distance, can we adapt our ideas of convergence? Right? Remember, up until this point, we always talked about convergence by talking about the difference in absolute value. So recall the definition of convergence for a sequence of real numbers. A sequence converges to a limit L if, and only if for every epsilon, there is a natural number n for which the following is true. If n is greater than or equal to big N, then xn minus L in absolute value is less than epsilon. So how can we adapt this notion of convergence to an arbitrary metric space, that is, a space where I have a tool to measure distances? Well, I'm just going to replace my old tool, the absolute value of the difference, with my new tool, the metric. So given an arbitrary metric space, and by the way, this is typically how we write a metric space, the set and then the distance function attached to the set. That's what makes it a metric space. So everything stays the same except that instead of the absolute value of the difference, it is the distance from xn to L is less than epsilon. Similarly, we can update our notion of Cauchy convergence. For sequences in R, our definition looked like this. A sequence is Cauchy if and only if, for every epsilon greater than 0, there exists a natural number n for which the following is true. If little n and little m are bigger than or equal to our natural number big N, then the absolute value of the difference of those two sequence entries is less than epsilon. Again, if I replace my absolute value difference with my metric, right, my new way of measuring distance, then I can retain the idea of Cauchy for any arbitrary metric space. If a sequence in the metric space x, d converges to a limit, then the sequence is also Cauchy. Now, you probably knew that already. In fact, we proved that that was true on the real line using the metric of the absolute value of the difference. So we've actually already proven it, and if you take that proof and replace every absolute value of a difference with the metric, you would have the proof for this theorem. So we'll omit it because you've seen it. Now here's where things get a bit out there. The converse is not necessarily true. If a sequence is Cauchy, that does not necessarily mean that it converges to a limit L. Now, it was true in R. We proved it. We did it last semester. So what are we missing in an arbitrary set X? If I just have an arbitrary set X, what are we missing that Cauchy is not enough to guarantee convergent? Well, I'm going to leave that question for you to answer. But let me give an example of a sequence that's Cauchy but not convergent. So consider the sequence 1 over n, right, where n is, of course, natural numbers in the sequence. And I'm dealing with the set of the real line except for 0. I've removed 0 from the real line. Well, that's okay. For no natural number, 1 over n is 1 over n equal to 0. So this sequence is clearly contained in this set of the real number line with the whole at 0. Now clearly the entries of the sequence get arbitrarily close to each other, meaning that it is Cauchy. However, the sequence does not converge to any number in my set. Right? If we were to look at the sequence on the real line, we would say, well, it converges to 0. But 0 is not in my set. However, with this set, I do have a metric, right? The absolute value of the difference. I can use my old-fashioned metric. I have a metric, I have a set. I've got a metric space, but my metric space has a hole in it. Now, if my metric space has the property that every Cauchy sequence is convergent to an element in X, then I have what's called a complete metric space, or what I like to think of as a metric space without holes in it. R is complete. It doesn't have any holes. That's it for today.